Gracias para esa introducción. Buenas tardes. Con ese micro me siento... Oh, no, un momento. Bien. Bien. Ajá. Con ese micro me siento un poco como uno de estos predicadores evangélicos. Y ustedes pueden decirme después si eso era una vocación alternativa para mí. Sí, no, excuse me, I meant to tell you that, claro, es que he olvidado, iba a decir que voy a dar esta charla, conferencia en inglés, pero si alguien quiere formular una pregunta en castellano, puede hacerlo. Euskera, hasta ahora, desgraciadamente, no entiendo. Por eso no he entendido mucho de lo que Inigo. Well, yes, I did understand what Igor said, and that was very nice. But I won't be telling you tonight a lot about, in fact, if anything, about what I personally have done. I want to give you just an idea of what's interesting about the theory of gravitation, and a little bit bring you up to date on what its implications are. And so, in effect, there are implications for the very large scale understanding of the universe, and that's cosmology. So I'm going to be telling you something about cosmology. And on the other hand, there are implications for the very small scale, the smallest possible scale. In fact, I'll be asking what that is. That will involve quantum mechanics, and at some stage it will involve indeed strings and brains and various other things. And I will say something about that towards the end. So the title that I originally chose, as you see, is Quantum of Attraction. It was a bit of a play on the James Bond film Quantum of Solace, but because, as we all know, these titles are translated into Spanish into something completely different. So, and in fact, this is not an exception here. But the alternative, the Spanish version there, I think, is a little bit more precise. As you see, the gravity in the large and in the small. I have to switch this on too. There we go. No, wait, that's right. Let's see. This should be full screen, so we don't really need these things on the side here. Maybe if I push this button. Well, I don't want to start pushing buttons because I've been through all of that this afternoon. Oh, very good. And oh yes, and that's the pointer. Yes, thanks. Yes, very good. There was an abstract for this talk, and I wrote the abstract, of course, before I actually put pen to paper to write the talk itself, which often happens, in fact. But I noticed later when I was reading over it that I'd actually used what some often called scientific notation for large and small numbers. And it occurred to me that not everybody knows what that is. So I'd first of all tell you what that means. So, for example, in the abstract, there were two numbers that appeared. One of them was 10 to the 27 meters. That's more or less the size of the universe. Now, what is 10 to the 27? Well, it's 1, and then you have 27 zeros. And you can see the point why we scientists like this notation. It gets very tedious to write out all those zeros. And if you have something which is 10 to the minus 35, that minus looks a bit mysterious, but that's just 1 over 10 to the 35, which in fact means you have 0, and then you have 34 zeros before you put a 1. It makes the budget deficit look reasonable by comparison. Well, the big one does anyway, not the small one. So there'll be various large numbers appearing and small numbers, and that's the standard notation for it. Well, of course, the two big names in gravity are Newton and Einstein. So before I do anything else, I just have to summarize. Here I've got one slide each to tell you what they did. So let's start with Newton. That's 1687. That's the date of the publication of his great book, the Principia, written in Latin. And what did he say? Well, basically he said, he said that every material body has inertia, and that's resistance to change of motion. Actually, he didn't call it that. First of all, he was writing in Latin, so he gave it some other name. But basically, that's what we call mass today. And there, in principle, different kind. Well, there was a point when there were people played around with different kind of versions and adjectives describing mass, but that's essentially, we physicists today just say mass. And then, of course, the other thing that he said was that there's a universal attraction between any two point masses. I should have said points in here. We imagine that there's some mass, say m1, at some point here over here, and there's another one over there. The distance between them is, say, r. And he says, well, there's a force of attraction between them given by this formula. Now, you're not going to see very many formulas tonight because, well, first of all, Newton never used them, actually. He wrote everything out in words. But there are a few formulas, the kind of formulas that you would see on a T-shirt. And so they have a certain aesthetic appeal, even if you don't understand any of the symbols. And just in case, you might see some of these things on T-shirts. So I don't feel, since you can see them on T-shirts, I feel that, well, I can include them in the talk. And here's one. So there's a very famous one. And of course, that introduces Newton's gravitational constant. So that was his hypothesis, and it explains an enormous number of things. It explains the motion of the planets, the comets. His friend Halley, in fact, used his theory to predict the return of the comet in 1758. Unfortunately, he died before it did return. But when it did return, of course, everybody said that's Halley's comet, and that's how it's been known ever since. And in fact, that may well be one of the very first predictions in science based on a theory. There were many predictions previously based on analysis of data, and you look for regularities, and you say, well, it went like this before, it'll probably go like that in the future. But this was the first real prediction based on a fundamental theory. And then, of course, it also explains the motion of the moon, in particular the eclipses. That was also done by Halley. Newton didn't bother with that. Then also the tides. That was one that Newton did think about. And in fact, one of the problems of the time was to explain why there are two tides a day rather than one, because most people thought there should be one, but Newton explained that why, on the basis of this theory, there should be two. And of course, famously, apples. And you might think, well, that's the easiest of the lot. But of course, actually, you have to be clever for that. And he was. But the point is, you have to realize that the whole mass of the Earth, as far as this formula goes, mathematically speaking, the whole Earth can be replaced by a point at its center. And then, of course, the distance r is the distance to the center of the Earth, and you put in the formula, and lo and behold, you find there's a complete unison between the terrestrial gravity and the celestial gravity. So anyway, that's what Newton did, and it lasted for about well over 200 years. Actually, getting towards after the 2nd century, there were, in fact, a certain number of discrepancies that started to appear. And one of them, in fact, was I've mentioned it down here, was the precession of the perihelion of Mercury. So Mercury spins on its axis, and the axis itself rotates. But if you compute how it should rotate according to Newton's theory, you discover that it doesn't accord with the observations. There was a discrepancy. So that was a well-known discrepancy around the time that Einstein appeared on the scene. Now, Einstein's theory of gravity